All right, here are a couple more trigonometric identities that we're going to verify, okay? By the way, the textbook that we're working with uses the term verify, but other textbooks will use the term prove, okay? What we are doing are proofs, right? We're proving trigonometric identities by applying other known trigonometric identities and thereby establishing the truth of some new trigonometric identity. Okay, so proving things based on the truth of previously proved things. That's like basically what math is all about, right? Here are two examples. In this first example, we have sine squared minus 1 over tangent times sine minus tangent. Those are all of some given input angle theta. So what I want to do is simplify the left side to the right side. Okay, I've set these all up so that the more complicated of the two expressions is on the left, and so I'm going to work from left to right. But I mean, if you encounter one of these and the one on the right seems a little more complicated, you can start with the one on the right and work towards the left. It doesn't really matter which way you do it. But I'm going to take the left-hand side here. What does that equal to? Well, the first thing I'm going to do is take this denominator and actually factor out that tangent. So in the denominator, I'm going to factor out the tangent of theta. What I have left after factoring out is going to be sine of theta from the first term, and then minus 1 from the second term, because it's just tangent, so if I factor tangent out, all I have left is 1. Sine theta minus 1. All right, interesting. That means my denominator has a factor of sine theta minus 1. My numerator is sine squared minus 1. Interesting. Sine squared minus 1. Isn't 1 the same as 1 squared? That's the same, right? Well, that means my numerator could be factored as well, because the numerator is a difference of squares. So if you remember, a squared minus b squared actually can be factored as a plus b times a minus b. Okay, that's a difference of squares factorization that we were working with, near the beginning of the semester, and you've probably seen that in other classes before. We can apply that idea right here. So this can factor as sine of theta plus 1 times sine of theta minus 1. Difference of squares factored out. So now we can see that the numerator and denominator have a common factor of sine theta minus 1. So that is going to cancel. And now we have sine theta plus 1 over tangent of theta. And that's what we were going for. That's the right-hand side that we were seeking. And so we did it. That verifies the identity. All we did was apply a little bit of algebra and canceling, and that verified it. So we didn't even use any other trig identities, which is fascinating. There's other ways that you could have proven this one that do use trig identities, but we didn't need to do that. All right, so this time, for the second one here, we have cosine theta over 1 plus sine theta. In this one, what I want to do is try to manipulate that until it equals 1 minus sine theta over cosine theta. I would say that neither of these two is more complicated than the other. In fact, there's a lot of symmetry here. It's just that, obviously there's sort of a reciprocating and then one of them is a plus and one of them is a minus. It's kind of amazing looking at these that it turns out these are always the same value. There's something going on here, right? And so I'm just going to take one side. I'll again start with the left side. And I'm just going to copy it down here. I'm going to show you a strategy that works on some other problems as well. Remember that I'm just going to pull it up here. Where is it? Here we go. Remember that the Pythagorean identity involves sine squared and cosine squared. So if we can get something involving sine squared and cosine squared, that might be more useful. Okay. And in particular, like whenever you have something like 1 minus sine squared, that's always equal to cosine squared, and 1 minus cosine squared is always equal to sine squared. These are both basically equivalent to the Pythagorean identity, but just with a term subtracted over to the other side, right? So if we can get instead of 1 plus sine, if we can get 1 minus sine squared, then we would be able to apply that. And the way to do that is to use the same difference of squares idea, except what we want to do is produce that difference of squares by multiplying by the conjugate, just like you do when you're rationalizing a denominator or we're working with complex numbers. We have this idea of conjugate. And the conjugate of 1 plus sine theta is 1 minus sine theta. So what I'm going to do is multiply by 1 minus sine theta in the numerator and denominator. To keep the balance, I'm multiplying by something that equals 1. But written like this, it is going to give me, my numerator is just going to be exactly what it is. I'm not going to do anything fancy in the numerator. It's just cosine theta times 1 minus sine theta. But in the denominator, since I have a plus b times a minus b, apply the difference of squares idea, and we get 1 squared, which is still 1, and then minus the sine squared, like that. And now 1 minus sine squared is equal to cosine squared. So now I can take this, apply that identity, and substitute in cosine squared for 1 minus sine squared. So let's see what that gives us. Cosine theta times 1 minus sine theta all over cosine squared. And now we can reduce that fraction because cosine theta is a factor in the numerator, and we have 2 factors of cosine theta in the denominator. So we're going to bring that down to 1 factor. So now we have 1 minus sine theta left over in the numerator and just a single cosine theta left over in the denominator. And hey, that is equal to the right-hand side that we were aiming for. So we did it. It's been confirmed. It's proven based on nothing more than algebra and the basic trigonometric identities that have already been established, in particular the Pythagorean identity. And there you go. So I think that's it. Yeah, that's it for 9.1.